Gabriel. Gabriel, vai. Ele é um colega de Coimbra. Gabriel é o organizador do nosso seminário.
Ok.
Aqui é o livro de
Presença.
Você quer colocar lá no seminário?
Vamos ver se está tudo em ordem. Não sei se tu consegue ser Não, tranquilo, pode ser.
E conheceu o André? O Eric? Ainda não. Ele tá falando trabalho de ingresso, conheceu o André faz ainda. É? Não, ele... Vai conhecer os alunos, né? Tava lá, Carol. A galera.
É, sim.
Deixa eu ver se eu tô aqui não. É que o André tem aula de noite, né? Ela não vai poder vir?
Se quiser passar para o de trabalho.
Deixa eu sentar aqui. Eu posso fazer a apresentação dele. Aqui vai estar o YouTube, né?
Isso aqui é de onde transmite.
Tá.
Tá bom, você faz a apresentação então?
Faço, pode deixar.
Eu dou uma breve introdução daí você entra ou...
Pode ser.
Tá.
Você pode falar do programa de seminários e tal.
Tá bom.
E aí eu apresento ele. Do público. E como é que você... quem é que está responsável pela transmissão no YouTube? É o Richard?
Já está transmitindo.
Ah, tá.
Vamos salvar, né? Acho que...
Não sei, eu apertei esse botão.
Ele fechou.
Ele fechou. Tá. Qual que é esta ou esta?
Então deixa eu dar uma olhada que eu tô...
E a Dani está por lá?
Não.
Ah, não, tem.
Não, melhor em português ou em inglês?
Como você quiser, acho que todo mundo está em inglês.
Tá ao vivo.
Tá ao vivo, né?
Mas não está indo transmitindo.
Ah, sim.
Tudo que a gente está ouvindo, falando, está passando?
Eu não posso falar mal de ninguém.
Não, agora não pode.
Som, tá com som? Porque tá sem microfone, eu não sei se ele tá captando direto aqui. Ó, o de cima vai pra frente, de baixo vai pra trás.
Tá com som.
Tá com som? Se você quiser,
Tem um delayzinho.
mexer o mouse, você tem que cortar e segurar. Ele sente o movimento, tá? Oh! Desce o drive. Espetacular. Obrigado.
Só me falta uma aguinha.
Será que
Tá. Não, você está com a distância de 1,5 metro. A Dani vai vir?
Não. Eu estava no telefone fora.
Não. Tudo bom? Tudo bom? Agora você conhece lá do Castle Meeting?
Assim,
Ah.
você viu lá.
A gente se viu lá, né? Que bom te ver de novo. Tudo bem?
Tudo. E você?
Tudo. Foi bom esse Castle Meeting, né?
Foi. Foi bem interessante. Quero ir no próximo.
Ah, sim. E a Croácia é muito bonita.
Foi lindo. Hoje eu tô torcendo pra Croácia, né?
Ah.
Vai ficar quanto tempo?
Eu vou ficar bastante tempo. Até fim de janeiro.
Vai ter o curso de verão, professor?
Vamos ver.
Os interessados.
Essa semana tem 2 palestras, hoje e quinta-feira. Vou mandar um.
Já mandou e-mail da de quinta?
Ainda não. É só para não confundir com o pessoal. Mas amanhã a gente já manda.
Amanhã é jogo da França, viu? Torcer pra França amanhã. Já reservei minha mesa lá no barzinho francês.
Pois é, você encontrou um bar francês.
O Felipe que achou pra mim.
Eu não conhecia nenhum, foi no Google. Felipe acha tudo.
Acha tudo.
São Paulo aqui, né?
Aí vi o nome, rendezvous, falei, pô, bar francês, mandei um e-mail, vocês transmitem o jogo, responderam na hora. Sim, a gente transmite o jogo e tal.
Mas tem outro bar, que é Marrakech, que é muito bom também.
Esse daí não é bom, não.
Vai estar bem propício de ser lá.
Eu vou chegar com a camiseta azul da França, sabe? Aí já não sei se eu saio vivo de lá.
O pessoal assinou o livro?
Muito bem. Mas eu não assino mais quando tiver saindo.
Depois isso parece que fica gravado, né? No YouTube não, eles dizem, isso fica gravado.
Fica gravado. A gente tem um canal de palestras do departamento.
Legal.
Começou na pandemia.
Pois. Tudo aumentou de Zoom, conferência na pandemia.
E agora a gente deixa gravado desde que a gente voltou da pandemia.
São todos seus alunos?
Não. Mas vai. E alunos do laboratório, praticamente, exceto a Ana e o Manuel. E o Marte. Tá, tem que se ligar o professor, começando a fazer muito barulho. Obrigado, Gabriel.
Muito obrigado, Gabriel. Vou ficar bem. Já é.
Estou fazendo a introdução, Gabriel?
Posso fazer a introdução? Sim, tá bom. Posso começar?
Lógico.
Pessoal, boa tarde a todos. Bem-vindos a mais um seminário do Departamento de Geofísica. A gente tem esse seminário hoje, excepcionalmente às terças, mas vamos ter outro também com o Eric Fonte na quinta, então estão todos convidados. E eu convido agora o professor Ricardo para introduzir o nosso palestrante de hoje.
Obrigado, Gabriel. O nosso palestrante de hoje é o Eric Fonte, professor da Universidade de Coimbra. O Eric foi um ex-aluno nosso, fez o doutorado dele aqui no IAG, em paleomagnetismo, concluiu em 2007. 6 ou 7? 6. E depois ele fez um pós-doc aqui também no IAG e seguiu para Portugal, trabalhou um bom tempo em Lisboa e agora é professor associado da Universidade de Coimbra. E ele trabalha em vários assuntos ligados ao magnetismo. Ele vai apresentar nessa semana 2 das principais linhas de pesquisa dele. Uma delas é o limite KPG e a outra é o magnetismo de espelhotemas. Então, agradeço muito, Eric, por ele ter vindo aqui para dar essa palestra ao vivo, presencialmente. E isso é parte de um convênio que a gente tem, a USP, com a Universidade de Coimbra, que permite a ida e vinda de pesquisadores, que foi assinado nesse ano. Muito obrigado, Eric, por estar aqui.
Obrigado.
E fique à vontade para dar a sua palestra.
Muito obrigado. Bem, como o Ricardo disse, primeiro, é uma honra para mim estar com vocês. Agradeço imenso a ajuda do Ricardo, que foi meu supervisor, meu mentor, meu pai científico. E é muita emoção para estar aqui com vocês, porque já faz 16 anos. E, portanto, eu sempre digo minha carteira de identidade é francesa, mas o meu coração é brasileiro. Fiquei muito triste por o Brasil não ter ganhado. Eu não sei se eu faço a palestra em inglês ou português, para mim tanto faz.
Como você preferir.
Talvez em inglês por conta do Matt.
Okay. I can speak in English, so yeah, it's okay. Okay. So this is works that I've been doing during the last 10 years. When I was a young student, I was always fascinated with these KT mass extinctions, the death of dinosaurs and so on. So when I finished my PhD thesis with Ricardo, I decided to study and apply some magnetic techniques to this fascinating stories. So, as you probably know, Jacques Sepkowski was a scientist who worked on mass extinction. Basically, he did a review of the number of species, genera, and families, and their number along the Phanerosaurus. And after making this this number, he realized that there is several periods of the Earth where the number of genera and species decreased abruptly in the time. And so this was like he characterized like the big five, the big five mass extinction. Okay. Oops. Okay. So we got the Ordovician, Silurian, Fresnel-Flammarian, the Permo-Jurassic, the Trias-Jurassic, the Cretaceous-Tertiary, and probably, as you know, we are entering in the next sixth mass extinction, which is the Anthropocene, where the human being is beginning to influence the climate and the biota. So, as you know, the uniformitarianism is the present, the case to the past, but in our case, we are looking at the past to see what can be the future prediction for climate change. So we are studying how the Earth reacts with global climate change and how we can be for our future. And the example I will bring to you today is the Cretaceous-Tertiary mass extinction, where we got two hypotheses of the bolide impact and the volcanism theory. The Cretaceous-Tertiary mass extinction corresponds to the death of dinosaurs, but also of ammonites, belemnites, rudists. It's about more than 76% of the species that abruptly disappear from the surface of the Earth. And so, if somebody told me what kills a dinosaur, it's a sexy question that journalists always ask. I would say we do not really know, because the fossil record in the continent is very incomplete. First, fossilization is exceptional phenomena, which is really rare. You need a very specific and peculiar condition to preserve the dinosaur. So we are mostly looking at the marine record, because in the marine record you got the record of foraminifera, and you have almost complete succession and complete record. So this is where we can really study how mass extinction works. Some paleontologists say, okay, it was something quite gradual, and so it cannot be only an impact. And some say, no, it's really abrupt, and so it's a single event, catastrophic and really fast event, so it can only be schistoscopy impact, and so on, so on. But you know, paleontologists, for example, there was a blind test in the 19 with a lot of paleontologists. They got the same samples, and all of them reached different conclusions because it's sometimes quite not often really easy to find the species in the sediment. But we have species that totally disappear. We have some species that survive, and we have species that appear after the mass extinction. And so the question is, what are the processes? What are geological processes that lead to mass extinction? And actually, we got several hypotheses. And one of the hypotheses is that anoxia sea level can really be associated to mass extinction. This was the idea of Allen in the 1992 from UK, who proposed or realized that many of the mass extinction correspond to rapid regression, and this can affect ecosystem, because you are changing and disturbing habitat areas, and because they are so fast that the species cannot really respond to this abrupt change. Okay? But in some case, for example, here in the last glacials, we have no mass extinction in here and here. So and it's not always easy to explain mass extinction with a single event, which can be the regression and transgression. But at the same time, if you look here, it can be impact, and about the impact, the unique mass extinction, which is definitively associated to an impact, is the Cretaceous tertiary boundary here, and the other are not necessarily associated to impact. On the other hand, you have, for each mass extinction, the correlation with large igneous province. I will explain later what it is, but it's huge volcanism that can be associated. But the KT is a peculiar case because you got an oxyous sea level change, you got a meteoric impact, and you'll have volcanism of large igneous provinces. So let's begin with the impact. The theory of the impact begins in the 19th with a paper of Alvarez, who actually was doing some survey in Italy in the Botacione section. And he discovered this feature by chance, actually. And what they found is that the boundary between the Cretaceous and Paleocene that find iridium anomaly. So iridium is really rare on Earth, really poorly concentrated, but it's highly concentrated in meteorite. So he supposed that a meteorite impacts the Earth and kills the dinosaur. And later they discover other markers of impact. Some of them are the nickel-rich spinels, which is also rich in meteorite. They found the tectites, which are melt material by the impact. They found this shocked cross. This structure are usually created by high pressure during the impact. And all of this in this really tiny clay layer boundary. And so this is how Alvarez and colleagues proposed the idea of the meteorite. But at this time, and here this is a record far from Gubbio. It's the GSSP section, the global section, stratotype section endpoint, which is El Kef in Tunisia, where we see the collapse of the biological activity. Let's say carbonate, calcium decrease abruptly. So do the isotopic composition of the carbon. We have the iridium anomalies, the mercury-rich spinels, and you have some gradual decrease of the species. This is Globigenera eugubina, which is typical of the lower tertiary, and this is Maiorensis. Now we use other species, but this was also recorded in remote section, not only in Bidar, in many other KT sections in the world. But at the time that Alvarez proposed this hypothesis, they did not yet found the criteria, the astrogram, the impact structure. And this has to late some 12 years in 1992, where they begin to discover that in the peninsula of Yucatan in Mexico, they discover the structure of the impact, which has been found by gravimetric data, seismic data, borehole, deep sea sediment, where they succeed in identifying an impact, and they date the rock, the melt rock, at 64.898. We will discuss this age later, but it was mostly the age of the KT boundary in remote marine section. So it was done. We got the iridium on the sedimentary record, and we got the impact on the other end. So this is a nice story. And a lot of papers have been published since, because it was easy to publish with such a sexy topic. And this is a paper of review of Schultz et al. In Science, where they make a review of all the marker in remote and section close to the impact. So you got something like it's interpreted like a tsunami-induced deposit. We will talk about this later. Then you have the typical iridium anomaly. And so this was probably global event, rapid, and proposed as the main killer of the dinosaur, and so on. The processes by which it can have killed the species here, darkening due to the dust emitting the stratosphere, it's like a nuclear winter. Okay, and acid rain due to the release of CO2, SO2, global wildfire, mega tsunami, so on, so on, so on. So they suppose that it impacted here, and it was deposited in the Yucatan Peninsula, several tsunami deposits due to mega tsunami wave, and that a lot of wildfire around the globe due to the thermal energy liberated by the impact. Many forest burns at the time, so it was, this is in French, the day where the earth burned. So this is a quite nice scenario, well shaped, but actually there may be some problem. So I'm not here to demystify the impact, to say, okay, no, it's not true, or I'm from volcanism. And some 10 years ago, it was really hard for us to speak about volcanism because the impact theory was so dominant, so people were not really prepared to accept that other processes can also have contributed. Now the new generation, I think they are more open and now really want to look at the data to see, oh, look, wait. Volcanism was the main cause of the mass extinction for all the big fire. Why it cannot be for the KT boundary as well? Okay. So, and how was the story of tsunami was? How was this question of wildfire and so on? So let's have a look. And let's have a look to the problem. The first problem is when somebody gives you an age for, I'll show you 64.98 plus 0.05. This is actually not really true. You always have to be really careful and conscious that it's almost impossible to provide precision of 0.05 million years for this kind of periods. It's almost impossible. Okay, you can have some error associated to the mean of several samples. This is analytic error or systematic error, the same geoscience. But behind this age, there is several error that you cannot see on the paper, but you must know. The margin of error is actually 300,000 plus or minus. Because the radiometric method, normally you can have several errors, which are, for example, related to the question of calibration between several laboratory. You have the question of all of this is made based on the standard. Okay, we assume that this is a perfect concentration of potassium, argon, and so on. But this standard has an error, marginal, percentage error, which is not taken into account when you provide the age, but it has, actually. Then, when you make the calculation, you have a constant of disintegration of radioactivity element. So potassium to argon have a decay constant of blah, 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 blah. But this decay constant also has its own error that you cannot see here, but it exists. And people are trying to push the limit more and more to have the better precision possible as possible. So if you make a sum of all of this, you have some 1 or 2%, you got this 300,000 error, which is 600,000 error in the age. So when you say, okay, the Chisco loop is 64 plus 98, it can be actually 65.2 or 64.5. So this is a lot, okay? So when you are trying to correlate it, an impact on the site and remote section, this is beginning to be complicated. But okay, on this time we've made a lot of advances in the last 10 years. We are now quite confident about the age of the KT boundary. We have two reference, which is Clyde in 2016, who used uranium geochronology in the Denver Basin in USA. We have the work of Courtney Spray, who did the Elk Creek Formation in USA. And these two ages are almost similar to the age of the technique, of the Chicxulub technique that has been dated.
So within some margin or error, we can assume that, okay, we are quite confident that the age of the KT boundary in remote section well corresponds to the impact. Okay, so this is good. There was an impact, it has been done accurately, and it corresponds to the iridium layer in the remote section. Good. What about the tsunami? I was always a little bit worried because it's tsunami, because I work in the Atlantic margin and there is no evidence of record of tsunami deposits. A lot of publications told, we have found it, but if you really look, if you are a geologist and look at the sedimentological evidence, you can clearly see that it's not tsunami deposit. And the story was built by Jan Smith, who actually made some comment of some of my papers. He's an impactist. He's almost retired, or already retired. And what they said is basically, okay, look, in Minbrau, Brazos, all of this section around the Gulf of Mexico, we have the impact spherules. So these are like small spherules coming from the impact. So they are EV, so they deposit first. And then we got a tsunami who deposits these 1 meter thick sandstone deposits. And then we have the iridium layer. Iridium is like dust, really heavy, then they deposit it later. So it's like a chronology, which seems to fit really well. And from basing on this, they build a story of tsunami. But later, some colleagues, Gerta Keller, principally, and Thierry Haddad, who is an excellent geologist, they visit all of this section. And actually, this section are a channel section on the platform, okay? And what you got here is, first you see below, you see this kind of features here. I don't know if you have any idea what can be this. Or maybe somebody has an idea, but these are paleosoils. These are roofs. Okay. These are bioturbation. So this really need time to do. You cannot really do this in fast. Okay. Then if you look at the sand, you clearly see here ripple marks. Okay. And you see ripple marks in one direction, another direction, horizontal lamination, then ripple marks and ripple marks. So you need time to do this. Okay, and you need waves and movement. Okay, so this clearly cannot be a fast deposition. Okay, never. So this demonstrated that basically the story of tsunami, at least in Mexico, has really some problem. Okay. I cannot say that there is no tsunami, but this is not what this geology told us. Jan Smith is a geochemistry. I'm not sure he knows something about geology, but we always have to look. We are studying rocks, so we have to look at the rocks first and see what they told us. And very fast, this is an example of a work of Claire Belcher, which is a really bright scientist who studied charcoal with specific technique. I will not enter into details, but the conclusion, she studies a charcoal deposit in Elk Creek in USA, and she demonstrated that basically no evidence was found in USA about wildfires. So she concludes that this finding indicates that the KT impact cannot have delivered a peak, the energy sufficient to initiate this wildfire. Okay? All of his work demonstrates that actually there was no extended wildfire in USA at this time. This is typically coal or charcoal or organic matter, but not from wildfire. So no tsunami, no wildfire. Yes, we have an impact, but was the Schisler loop the unique trigger? That's the question. So now let's try to look at the large igneous provinces, and this is an example of several of these lips, large igneous province, which is an extremely huge accumulation of lava flows in a quite short geological of time. Okay, so we have several. This is a Siberian Traps, for example, that are associated to the Permo-Triassic mass extinction. We have the Central Atlantic magmatic provinces here, the Newark and the Morocco's, which correspond to the Triassic-Jurassic mass extinction. We have other, you got the permanent trap, but it's not associated to mass extinction. And we have the Deccan Traps in India, associated to the Cretaceous-Tertiary mass extinction. So this is a very famous picture of Vincent Courtillot, who make a correlation between the age of mass extinction and the age of large igneous province. And this is a almost perfect correlation. Okay, so, and this is some kind of review I recently published with a colleague, David Bond, where in each of these mass extinctions we got some mercury anomaly, and you will see later why these mercury anomaly are so important for us right now. Okay, so India, Deccan Trap. This is a photograph of the Deccan Trap. We are talking about 3,500 meters, 3 kilometers and a half of lava flows. Okay, in an area which represents almost the size of France. So imagine France recovered totally by lava. So it's not volcanoes. These are a lot of volcanoes. Okay. If you look at the original size of volume, it's 1 million cubic kilometers of lava flows, and the amount of sulfuric acid and so on is really huge. Okay. The effect of the volcanism can have several effects, and it can act on different time scale. You have some cooling effect, which is at the short term is linked to the diminution of the solar radiation, okay, due to the dust. You have global warming due to the amount of CO2 that is emitted in the atmosphere. And you have a long-term also cooling effect, which is basically due to the, when you're supplying CO2, CO2 is an acid transformed in carbonic acid. The weathering of silicates consumes the CO2, and so you are consuming CO2, you are decreasing the greenhouse effect, and you are decreasing the temperature. But the main is probably acidity. And we are all talking about acidification, because the amount of chlorhydric acid, fluorhydric acid, CO2, SO2, when oxidized with the atmosphere, creates some acid rain that can acidify the environment, kills the primary productivity, and if you kill the primary productivity, all the chain is disturbed. So we know that it can have effect on the ground. But we don't really know exactly, because there is no similar phenomenon during human being. Okay, there is no lips, actually. The most recent example we can have is the Laki eruption. The Laki eruption took place in 1783, and it was a year without winter. It was a year where there was a decrease in temperature. All Europe was covered by clouds. You have a lot of acidification, acid rain. This is Iceland, okay. It's where the mid-oceanic ridge outcrop in the continent. So we know that at this time you have historical records that it really impacts the climate on Earth and agriculture and human being. Now, if you look at Laki, the size of a Laki, and if you look at the size of the Deccan Trap, it's obvious that it should have some impact on the Earth, on the climate. So now this is the second problem. We got lava on the continent, and we got the marine record. How we can correlate them? I mean, we again need good age, and again we are coming back to this precision. How able we are to provide such a precision 66 million years ago. Okay. So the prerequisite is that to have contributed to the mass extinction, the volcanism has to begin before. If it begins after, obviously it cannot contribute. So we have to date this. and see how we can correlate with the KT boundary. The first work of paleomagnetism came in 2007 with Alice Chenet, who was a student of Vincent Courtillot, who did his PhD thesis in the Malawak-Bashwa section. And she found that 80%, this is the thickness of the Deccan lavas flow, 80%, which they call phase 2, was more or less date at around 60 and something million years in the Crohn 29R. Okay, so this was more or less, according to the age of the KT they have, precede the KT boundary, and thus the main pulse can be more or less correlated to the KT mass extinction. Now, we don't use anymore because we have since very precise age on uranium leads. This is a work of Blechon, which is from Princeton. And what they did, they date the zircons, detrital zircons, between lavas, okay, and provide very precise age. And so, as I told you, we know the age of the KT boundary with the age of Klein and with the age of Courtney. And now we know the precise age of the lavas flow. So we can say, okay, the KT boundary is more or less correlated with the Pollack-Bood and Ambenali section. Remember these two names. These are the Seeker section, the Seeker formation, okay, Pollack-Bood and Ambenali. So in this case, yeah, we can say that Deccan traps can have contributed to mass extinction because there is a temporal causal relation between two. Then a little bit later, we got another paper from another school, which is the school of Paul Ren from Berkeley, one of the most famous labs of potassium, argon, dating. And they told a different story. They date the feldspath, potassium and argon in feldspath, so they date directly the lavas. And this is a formation, and this is the cumulative volume of lavas flows. And these are the age. So this is the age of the KT boundary. So this section begins to erupt before the KT boundary, and then you have an increase, rapid increase in the volume of lava just after the impact. So what the story they said is basically the schist loop induced a state shift in the volcanism. Imagine you have volcanism, and on the other side of the world you got an impact, and this you got higher, much higher eruption rate. Okay, but they still think that the main pulses are after the KT boundary, meaning that the contribution of the Deccan trap in this case is lower. Okay. Of course, Blechon and colleagues come back to India, collect more samples, and publish a new model. This is a Bayesian model. This is the age model they produce. So this is the age of the KT boundary with the margin error we know. And this is a pulse of Pollack-Bood. So these are eruption rates. So this is something that is really important. As I say to my students, if you drink one beer per day during the week, you're fine. If you drink all the beer of the week during 1 hour, maybe you will not be so good. Okay, this is a little bit the same. If you erupted a lot of lava flow in a very short time, the time for the Earth to respond to this is shorter, is difficult. Okay, this is the residence time of particle. Okay? If you make some eruption, wait a little bit, but this will have no effect. Now, if you erupt all the lava in a short time, so yes, this will be difficult for the Earth to accommodate. And what you find is that the main pulse of Pollack-Bood just precede or is synchronous with the KT boundary. So this was really important results. Okay. And this would be Avenani. And close to this, what they show is a cooling effect here with the temperature estimated by oxygen isotopes and a decrease in the osmium ratio. to make it fast, osmium ratios 188 can be supplied in the marine realm on two ways. It can be by impact, okay, but this would mean that the impact is before. Or it can be, it is usually contained in igneous rock, in lava flow. So when you are weathering a lot of lava flow on your continent and you are bringing this eroded material in the ocean, you are bringing more osmium 188. So you are decreasing the ratio of 187, 188. So this is almost concomitant with the dating of the big polar group pulse. This is a wonderful model. I love it. Not only because these guys are my friends, but yeah. Of course, for Ren and his team, make another paper in Science as well, with more dating. And they say, okay, more or less, we have the same model than before, but with more data, and the conclusions are mostly the same. They got the major volume just after the KT boundary. Okay. So we are at the period where we think that dating is perfect. We can date everything with really high precision in a perfect world, but we have two dating models looking at the same thing and tell you two different stories. Okay. One at 300,000 years of error, which is a KRR, potassium, but the advantage is that you date directly the lava in the feldspar. You Raman lead, you have only 30,000 years error in the age. But you are post-dating the lava because you are studying the zircon coming from the erosion of the lava. Okay. So you have advantage and inconvenience. But clearly, you have two distinct stories. So at the end, we've got okay, the record of extinction. We know that we have an impact that corresponds to the region layer. We have the Deccan Traps that probably begin before and encompasses the KT boundary. So now, what of them really killed? What was the contribution of each of them? Honestly, I'm not sure we will be able to answer to this. It's really difficult because we are looking to two catastrophic events that occur in a very, very short time of period at the scale, at the geological scale. I'm looking at the time. We try to make it faster. So now I will a little bit show you some of the work we conducted in the last year. So if you look at several sections, you have several features here which are interesting. This is, for example, decrease in species richness in temperature estimate for Paleosol in Dakota. We have a clear decreased cooling effect observed in the Baltic foraminifera, in the Atlantic. We have the osmium decrease. All of this seems to correspond to this big pulse of polar group. And we have something here in magnetism, which is an interval of low magnetic susceptibility. And at the time when I looked at that, I mean, this was published by Elwood, and I looked at it and thought, oh my God, this is exactly at the same period of these other features. There must be something to explore here. Okay. It's not coincidence. So I studied several sections. I studied the KT boundary in Bidar, in Associado, in Zumaia. So this is in France, here. This is, so it's related to Atlantic Ocean. This is another basin in the Tethys. This is a nice section because it's a place of nudists. They like to go there. So it was sometimes hard to go there and drill because people were staying exactly on the KT boundary. This is a place where, for who likes the Game of Thrones series, they, this is what I think the episode 6 or 7 was realized in Zumaia, which is a very, very nice place. You got several GSSP here. It's a really, really nice place. Okay, so this low magnetic susceptibility interval, I also find it in BIDAR. Okay. So really fast, you probably know what this means. What controls magnetic susceptibility? Magnetic susceptibility is a relative abundance of dia, para, and ferromagnetic minerals. So it's mostly calcite silicate in the diamagnetism. It's a clay mineral for the paramagnetic, and iron oxide like magnetite in the ferromagnetic. But what really controls it? Normally this slide is for my students, so I ask them to tell me what controls, and they try to respond, but I'm short in time. So basically the first is the lithology. If you have carbonates or igneous rocks, of course, the lithology which controls the magnetic susceptibility. The second point is the composition of the source. If you have big mountain of lava flow, probably the sediment inherited from the erosion of this rock will have high content of magnetite and high magnetic susceptibility. Then we have the sea level change, okay? Because when we are in low stand system track, you have a large area of erosion. You are breaking a lot of terrigenous material with a real small available space for sedimentation. So you have higher detrital content, higher magnetic susceptibility. When you have high stand system tract, you have a big space of accommodation. You have more carbonatic sedimentation, few detrital responses, so you have low magnetic susceptibility. This is how cyclostratigraphy works when we are looking at this rhythmic section. Okay. This is in a perfect world when the rock is not affected by diagenesis, because diagenesis can affect, obviously, as you well know this, transform magnetic mineral or creating new magnetic mineral, and then it's a mess. But during sedimentation, we can also have some change, okay? Like environmental parameters. And this is how environmental magnetism works, because all of this depends on the oxidant reduction potential works and of the pH. Because magnetite can be stable during billions and billions of years, but it can rapidly dissolve if you decrease the potential redox. I mean, in organic-rich sediment, black shales, magnetite dissolve, promote iron-free, react with sulfur from bacterial activity, form pyrite. This is what black shale have a lot of pyrite. They have no magnetite and no magnetic signal. We do not really do P-mag in black shale because we know that. But acidity, we don't really know, because to have something lower than 8 or 7, for example, we all of us are saying we have acidification of the ocean. But the ocean is not acid. The ocean is just less basic, less alkaline. But it's not acid, because the system is rapidly buffered by carbonate precipitation dissolution. Okay. Okay, so this is Gubbio. I would like to tell the entire story, but I think I will not really have time. But this has been interpreted by Lowry in 19 by percolation of organic-rich fluids. Okay, you got the impact. Everybody died, so we have accumulation of organic matter. Then you have percolation of fluid downside, and you are dissolving iron oxide, and you got these colors, and you have no iron oxide and low susceptibility. So I try to see, okay, first, is there any lithological change? No, these are carbonates and these are carbonates. So this decrease is not controlled by lithology. Sea level change is too small to be controlled by sea level change. Composition of the source is the same because we are in the same place, so there must be something other. Oh, actually, as Laurie said, or there is something else. So this is just to show that the composition is not really so different. At Bida also, these are Mars, these are small, these one are a little bit more reddish, but probably because of magnetic mineralogy, but the composition is almost the same. In Zumaia, always, you can see the calcite content, you can see the clay mineral and quartz. There is no specific change in the mineralogy. Lithology is the same, but you can see some decrease in the magnetic susceptibility. So now if we look at BIDAR, if we want to see if it's not the lithology, it can only be the magnetite. There is something wrong with magnetite. How can I know that? To know that, you probably know that we use magnetization. So these are isothermal remanent magnetization curves that are later in mixing, and then we show that in the low magnetic susceptibility interval, we got a drastic decrease in magnetite, soft, we can call it soft magnetite, and the hard magnetite totally disappeared. So what's happened to this magnetite? What disappeared? The same rocks. Okay. And another feature is the magnetosome, magnetotactic bacteria. Okay. You probably know this typical central narrow reach that is typical of non-interacting single-grain magnetite. Typical of the biomagnetite. The biomagnetite usually like to live at the oxic and oxic interface in the ocean, okay, and has this kind of signal. So with a colleague, Sasha Balashevich, we make some forks in Bidar and Gubbio, try to see what's happening. And these are really interesting results, because what we can see is that in the low magnetic susceptibility interval, biomagnetite totally disappear. Okay. And the most interesting is that just below the KT boundary and at the KT boundary, they are present. They are here. This means that the Lowry hypothesis of the dissolution of magnetite from the KT boundary by percolation over here, it's not valid in this case, because otherwise it should be absent here as well. But there is. So the disparition of biomag is related to other things. This is the same in Bidar. In Zumaia, we got the central narrow ridge, and here we can see that the biomag or the detrital mag, or whatever, decrease before the KT boundary. Okay. So this is magnetic susceptibility, and we clearly show that here the magnetite dissolve before the KT boundary. This was our interpretation. It may be not the best, but I think it's valid. How we can dissolve the magnetite in the ocean? It's almost impossible, because I told you the pH is buffered by carbonate precipitation dissolution. So the only way is to dissolve it before it arrives to the sedimentary basin. And to have such a low pH to dissolve it, you can have this with acid rain. Because acid rain, the pH of acid rain can be 3, 4. We have a lot of examples of acid rain from Italia, from Vesuvius, a lot of volcanic event recent when we measure the pH of the acid rain. So the idea is that during the eruption, you release a large amount of acid that give acid rain, dissolve your magnetite on the continent, and your sediment is magnetite depleted, and you lose your magnetite. And now how we can explain the biomagnetite? But it's not really difficult, because if you are bringing such acidity, you probably move your oxic and oxic boundary, or you will reduce productivity. Okay, because productivity is basically also controlled by the nutrient you are supplying in the ocean. So if you are disturbing this system, probably the chemical line here will also change. And the biomagnetite that was happy before will abruptly die. Okay, so this was when I began to work with. It was in 2000. I began to work in 2011, and this was in 2014. And when I was looking at these rocks, I also find something really curious. So this is really exotic, because there is no other paper really about this. I'm pretty proud of it, because it took me 10 years to prove this. Okay, so you have to be in the system. You got to perseverance in French. I don't know the English word, but okay. So what I saw is a mineral. It has chloride and iron, and this mineral only in the sample where I have this low magnetic susceptibility, not below, just in the same interval. And with this kind of shape, it gives us the feeling that it's like pretty like particles that can easily fly. wow, can it be aeolian particle from volcano? I don't know, maybe. But what can it be? Chlorine and iron. You have not so many possibilities because the chlorine ion is really big. So to be able for a mineral to accommodate the space for chloride, you need a specific crystalline structure, which is called hollandite structure. You don't have in hematite or goethite, but akaganite has this tunnel structure that is able to accommodate the chlorine inside. Okay. But normally it has never been observed as a specular large mineral. It's generally observed like this batome, this what can be the name in English? This baguette. I don't know. Okay. Well.
We understand baguette.
Okay, baguette. You understand baguette? Okay, it's a French word. Okay. These are synthetic akaganite. Okay. I say, wow. Okay. It can be a tadana. I have to prove it. I need to prove it because when I show this to people, they say, "No, well, this is you have chlorine everywhere. It's salt from marine." No salt. I should have sodium Na in my spectra. I don't have. Let's go back here. You don't have sodium. You just have the chloride. The calcite is because here are the mapping also. You can see the mapping. And you can see the chlorine is on the mineral, is not on the matrix. Okay. But it should be associated to the mineral. So where can you find this akaganite? The first is a product of it's a product of corrosion of steel. When people working with prehistorical objects from the ocean, which is made by steel, when you take it out from the water, from the ocean, you react with salt, with oxygen, and you make corrosion. And this corrosion is one of the main processes to have akaganite. But we don't have steel with dinosaurs. Steel is human. Okay, it cannot be from dinosaurs. The other one is from March. It's really interesting. A lot of people work on this because they saw that the hematite is actually the product of oxidation of akaganite. They thought that akaganite was the main product there because of very peculiar condition. Because to precipitate akaganite, you need oxidizing condition, hyper-chlorinated solution, a lot of chlorine, hypersaturated in chloride. You need free iron, and you need very acid pH. So another possibility is akaganite in meteorite, but this is very well known. It usually have nickel. It always have nickel in the akaganite of March. Mine don't have nickel in the. And the last example, I finally found a paper. Wow! Finally, I found a paper from 1977 from Johnson, who studies the volcanic fumaroles in White Island, and they find akaganite linked to this volcanism. Wow, that is the key. Okay, that is possible. So now we have to be able to identify this akaganite. So I did a talk in the IPG in Paris, and I meet a colleague which is Julie Carlu. Oh, it's really interesting. We can do some fib measurement, and we can do something of okay. And later I talked with this Céline Remazet from La Rochelle, who is specialist with akaganite from corrosion, and she's working with micro-ramen, as we talked before. And okay, but how we can do this? I need to first find a particle and told you, okay, this particle I make a cross and send them the sample. Okay, here you should find one if you are lucky. Okay, and she find one, and she make the micro-Raman spectra. This is a typical spectra of akaganite, the reference, and these are the spectra of this mineral. So this gives a really good proof, evidence of that this mineral was akaganite. Then later we made a FIB section, a focused ion beam section. This is something like that. Look at the scale. This is 300 nanometers, so it's like a thin section, but when you open the box, you don't see something where it is a thin section. Okay. But by doing this, you can later observe this with a team transmission electron microscopy. And what we can see is this baguette here, and porous void, so it's something not consolidated, compatible with something that happened in the atmosphere, and with the composition of chlorine and iron, and again the baguette. So we finally succeeded in demonstrating that this was acaganite. Acaganite cannot be formed in any place. It needs acid conditions that we have in the volcanic plume. We have iron because we have several compounds in emission that have iron-3, iron 2. Okay. We have water in the atmosphere, and so we have HCl a lot. So we have all the elements, a perfect chemistry, a cooking pot where we can precipitate acaganite. So a lot of people told me, oh well, Deccan volcanism is not explosive, it's eruptive. So how you can transport this from Deccan Traps to weather? There is a paper by Kaminsky from EPG of 2010 that calculates some numerical model that if you have successive constant eruption, you create like a buoyancy current, a heating current. So it's not explosive, it's just like something very hot that is growing, and bring your particle up to the stratosphere. Once you are in the stratosphere, this is a highway for alien particles. They can make the round of the Earth in 3 days, something like that. So it's really easy for them to be transported. So the idea is that it's creating the Deccan and then transported to remote section. So now I have the low magnetic susceptibility, and I have acaganite. This was in 2017, so I was even more happy. But the most powerful evidence when we measure mercury in these sediments. Because mercury can be produced by anthropic activity or volcanism. At the time of dinosaur, it can only be volcanism. It's emitted as elementary mercury, Hg0. Then it reacts with the atmosphere to oxidize into Ag2+, and then it's fixed by organic matter or pyrite or sulfur compounds. Okay. And when you have volcanic events, so you have the mercury from the emission of the volcanoes, but also you are from the burning of all of your organic matter pool, that we also liberate even more mercury. Okay. So we measure them in BDAR. And the place where we got the low magnetic susceptibility, where we got the acaganite, we have a nice anomaly is mercury. Okay. To sell this as volcanism, you have to measure the total organic carbon. Okay? Because actually what's happened is, what you can have is simply the supply of organic matter that is rich in mercury previously capped. Okay. But in the case it's volcanic, it's directly deposited from the atmosphere. You should not expect a correlation between total organic matter and mercury. So you always have to measure organic matter. And the organic matter actually is really low. And there is no correlation between organic matter and mercury, suggesting that mercury was deposited by the atmosphere. And so this is now one of most of my city paper I have, and because it's a really strong evidence of the beginning of the Deccan Traps, and it's all. We also find this in other section. I will show. Where is this one? And it perfectly correlated with the polar pools dated by Blanchard, demonstrating that it began just before the KT bomb. Okay. Okay. Then we published a recent paper recently also to show that, because Jens Smith again say, oh no, this mercury is also come from the, you can have mercury in impact, in meteorite. So when he saw my paper, he said, no, this is mercury from the impact that percolated downside. And I make a reply, it's good, with comment it's good because you always have the last word. So we respond, but later I need to prove this. So what we do is to measure some very mobile element, okay, like vanadium, copper, zinc, that are easily to remove by percolation. And what we can see, none of this element is percolated downside. Demonstrates that this mercury cannot be from the percolation of fluid from the KT bond. And now people are trying to use mercury isotope, which is more difficult to measure in practice. There are really few laboratories in the world able to do this. But it seems that depending on the isotope, you have a typical signature for atmospheric or terrestrial, or if it's for volcanic emission, or if it's for contract. This has been published in 2021. And this is the final models with acid rain dissolving magnetite, mercury, and akagonite deposition. And now I say, okay, I can go to study other things. I think I close the topic. I will go to study spelotech now. Thank you very much. Hope it was not too long.
Thank you, Eric. It was a really nice presentation.
Yeah.
So let's open for questions. Everyone? Are these characteristics of the mercury and low susceptibility also observed in other limits?
In other limits, first I've tried to observe in other section in KT. Yeah, I do not systematically found it. But there is several regions. What we know is the Earth is complex. Climate is not the same at any place in the Earth. You have atmospheric current, you have not necessarily the same condition in any place. So I just find it in this place and not in other place. And for other mass extinction, I did not really try, and I'm not sure people try to do it.
Because of course it's a whole work.
Yeah, it's complicated because many of the problem is that it's really, people think that you just have to go to the section, make them relevant, and you get the story. But there is a paper of a guy, I don't remember, it told we have more gaps in the geological record than completeness. So it's really difficult or rare to have a complete section that record really all of the time. So it's sort of, I think that she was just really lucky. It's a question of luck. But no, nobody find it in other places. And I did not try yet.
So your work's not finished.
No, maybe not. Yeah, you're right. Maybe not. Maybe not.
Thank you, Eric.
Eric, is there any evidence of akagonite in other volcanic plumes or anyone
No.
that has studied that?
No. And this is another question of chance. Because if I did not, I spent many hours under the microscope. And imagine you are spending 10 hours and finally you find one particle in 10 hours. Wow. So if you are not curious, if you don't insist, it's easy to don't see nothing. Okay, so generally people have few money, few time on the microscope, they only get 2 hours, they go to what they want to see. When you are going to purpose, you just want to see what you want to see. But when you are trying to have open-minded to search and you have time, you have money, you can spend a lot of time, yes, you can, but it was really rare, really poorly concentrated. It's something that is below 0.1 weight percent. So maybe it exists, but nobody else finds it.
But because there are some people that collect samples from volcanic clouds.
Oh yeah, I asked who reviewed my paper was Tamsin Mather, who worked a lot with collecting, and she never saw that before.
Okay.
He never saw that before. So, yeah, still a mystery.
And the other question is how it survived the acidic environment.
The hydroxide are much more resistant than magnetite. Okay, if you take a diagram, a pH diagram, you see that hematite can survive much more than, because it's a hydro oxide. This is the hydroxy oxide, which is usually more resistant to acidification because it is formed under acidic condition.
Mm-hmm.
Okay, it need pH of 3, 4, 5 to 6 to be formed. So obviously later it resists to acidic because it's.
Yeah, but in the alkaline environment of the ocean it would resist anyway.
If you don't have reducing condition, I would say yes. Okay. Yes. Otherwise, you need to reduce it with with reducing condition with organic-rich matter sediments. Yeah, because this was a question: how I can dissolve magnetite and not dissolve akagonite? Because magnetite is dissolved on the continent, and akagonite is supplied by atmospheric.
Yeah. I have a last question.
Yeah, of course.
What do you think is the carrier of the mercury in this low magnetic zone? Because mercury must be somewhere.
Yeah.
Connected to clays or
Clays.
organic matter or clays.
Okay. Because clay are it's easy to fix mercury with clay, but of course it has to be fixed by something.
Yeah.
Okay, and it can be fixed. There are some papers that say it's sulfur oxide, but in this case we have no pyrite, not so much sulfur oxide. So it's probably by clay. Yeah, it's probably by clay.
Going back to the purported tsunami deposit, your arguments against that were quite convincing. But you mentioned at the beginning, I think, that beneath that you saw impact spherules, or there are reports of impact spherules, and at the top is the iridium anomaly. So I wonder how you...
They are below.
Both the iridium anomaly and the impact spherules? I thought you had a plot where they were...
Now you have first the impact spherule, then the sandstone, then the iridium.
Right,
Yeah.
so if that middle bed is supposed to be a very long span of time, how do you otherwise explain the impact spherules? Do you think those are misidentified, or they belong to some
Actually,
other-
you can. I have other slides. I did not put here because otherwise it should be too long. But they make some other drill core in some section there, and you can see several levels spherules, because spherule is something very common. It can be bacterial. It can be. There is a lot of process to make this kind of spherule. So it's probably not. Maybe not from the impact. Okay. Maybe they are here. It's not from the impact. There is a paper by Keller 2003 where she proposed two hints based on the fact that they discover two level spherules, and they say, okay, now it's not one, it's two. But later, well, we don't know if we have two, but we know that you can find this spherule everywhere. Okay. Maybe you have other spherule inside the tsunami, but I think these people just want to use what makes the scenario seductive.
My question is about the magnetoplastic bacteria, the signatures that you found. I'm not familiar with the paper that you have published that, so I was interested if, do you have any other evidence besides forks for magnetoplastic bacteria in those rocks? Because when you think about, not that it would change, and I don't know exactly how it could change the model, but in fork diagrams, the central reach is not only contributed by magnetoplastic bacteria, but as you said, by non-interactive single domain particles. And in a system of carbonate rocks, you can expect particles to be very far apart from each other. So it's not hard to have non-interactive single domain particles in that. So it was just a curiosity, and if you had used other techniques or other ways to see if those magnetoplastic bacteria were there, or if it's just magnetic evidence?
I don't have. I was supposed to, with a colleague from Lancaster, Barbara Mayer, who has specific device to try to separate them. And I was supposed to send her samples, and we never did that. But I would have been happy to do. And later, well, I never to confirm that. But if I understand, you think that you can have other way than biomag to produce this central weak, and it's true. We now have evidence that you can have some really fine-grained magnetic in some sediments that can produce the same signal. I agree with you. But yeah, in this kind of environment, we also know that it's frequent to have this kind of bacteria. So, and normally the magnetite here is detrital is larger. At least what I have observed under the microscope, these are larger magnetites that probably have no contribution to the magnetic signal. So this really non-interactive signal domain should be something very tiny that I was not able to observe under the microscope. So it can be, it's probably biomag. But you're right, it would be important to confirm by observation.
Yeah, I understand the thing about the size, but if the particle is like too rounded, or if the particle is like too iridic, you have the contributions of other anisotropies, and a really large particle could have an important magnetic contribution similar to something that would be normally detected as a multi-domain particle. So that's just a curiosity, because usually it's very hard to see direct evidence, and when I say direct evidence, actual microscopic evidence of magnetoplastic bacteria, and basically because we usually see the central ridge as a signature for magnetoplastic bacteria. But I think it's a beautiful model, and it's very, very interesting, the correlation between the loss of susceptibility and also the disappearance of the focal signals.
Yeah.
Just a curiosity.
Yeah. But yeah, maybe in the future, I say I'm not working anymore, but who knows? Maybe probably I will try to, because it's something I would like to do. But it's really time consuming. You need to have somebody who is able really to separate this. And with flocculation in clay mineral, because it's more, you have a lot of clay mineral, it's really hard to unflocculate them and be able to separate them and find the...
Thank you.
You're welcome.
Anyone else? Okay, so on the YouTube channel, Omar Ernesto was watching. She's congratulated your presentation.
Where is your camera?
There.
Temos que almoçar juntos. Já te mandei uma mensagem para nós combinar almoçar juntos. Estou te esperando.
Now it's recorded.
Fantástico.
Okay, thank you everyone for coming. Thank you, Eric, for the presentation.
Muito obrigado para vocês.
Muito legal.
Gostou?
Muito bom.
Pois é bom que depois de 10 anos você consegue realmente demonstrar a ideia que tinha inicialmente 10 anos atrás.
É muito bonito também.
Nossa, é muito interessante. Muito legal, tudo em engajamento lógico, né? Nossa,
Sim.
apresentação maravilhosa. Adorei.
Obrigado.
E a palestra está muito bem montada.
É.
Tá muito, muito bacana.
Obrigado, muito obrigado. Então, também é treinado, também já apresentei isso muitas vezes.
Muito legal.
You like it?
Very nice.
Yeah? I'm good, I'm happy.
So I have another question about to follow up with what Alison asked. So why do you think the magnetoplastic bacteria are disappearing? So you showed that they present deeper in the section, and then you have this gap in the, where there's no vacation. And then they start appearing again before the cave development. Why do you think, and I understood the argument correctly, that it's really the other background is all that coming from the environment that was giving you eye magnetic susceptibility, so you see this low magnetic susceptibility, origin is signal to stop. But you still have
No, because the biological product you don't have supply, you are not supplying nutrients. Você tá aí na onde agora?
Não, vou deixar minha.
Ok.
Meu casaco.
Tá bem. Eu vou agora.
Obrigado, hein? Obrigado, até quinta.
Tá bem, até quinta. Well, there is two possibilities. The first is you are changing, they are very sensitive to the axic and axic boundary. So if I go to make a change this blue, it will change the area. This boundary will change. They can not have suitable condition to live. The other is because you are killing the primary productivity of the ocean, you are not bringing any more nutrients for some species to live. What we see, for example, in the Magmatic is only